Okay, next up is question 10, surface number 2. Okay, this is the surface described by the equation x squared plus 4y squared plus 9z squared is equal to 36. This is what's known as an ellipsoid. And so just like for surface number 1, we're first going to describe the traces of the surface and then put them together to sketch the surface in R3. All right, so for part A, the y-z traces. This is where we set x equal to a constant. So that gives us the equation c squared plus 4y squared plus 9z squared is equal to 36. And I'm going to go ahead and subtract c squared from both sides. So we get the equation 4y squared plus 9z squared is equal to 36 minus c squared. All right, so noticing here that the expression on the left-hand side is non-negative for all values of y and z, that implies that this right-hand side also has to be non-negative, and that's going to happen precisely when c is greater than or equal to negative 6 and less than or equal to positive 6. Okay, so if I go ahead and divide both sides by 36 minus c squared, okay, I recognize this equation as the equation of an ellipse. Okay, it looks a little messy here, but it's y over the root of 36 minus c squared over 2. That over 2 comes from the fact that there's a 4 there in front of the y squared, plus the quantity z over the root of 36 minus c squared all over 3. Again, that 3 is coming from this 9 here. So that quantity is squared, and that sum is equal to 1. Now notice here, okay, I have to rule out the cases when c is equal to either plus or minus 6, because there the right-hand side of this equation up here would be 0, okay? And I can't divide by 0, of course. Also notice, right, that if the right-hand side of this equation is 0, that implies that y and z must both be 0. So in other words, when c is 6 or negative 6, we're looking at just a single point there for the y-z trace. That's when we're at the origin. Okay, so we get this family of ellipses here, right, all centered at the origin. And these messy expressions are describing the semi-major and semi-minor axes. Now, since we're dividing just by 2 here, the semi-major axis will be along the y-axis, and the semi-minor axis will be along the z-axis there. Okay. Also, I want to highlight the case when c is equal to 0. So if I set x equal to 0, okay, that's looking at the intersection of our surface with the yz plane. So if I set c equal to 0, okay, notice the semi-major axis would be what? Would be just the root of 36, which is 6, divided by 2 would be 3. So the semi-major axis, okay, in the case when c is 0, would be 3, and then the semi-minor axis, well, it'd be root of 36, which is 6, divided by 3 would be 2. Okay, so we're going to reference this specific cross-section of our surface when we go down here to sketch our graph in R3. All right, so then moving on to part B, pretty similar here. We set y equal to c, so we get the equation x squared plus 4c squared plus 9z squared is equal to 36. So again, I'll move the 4c squared over to the right-hand side. And now, again, the left-hand side, right, it's a sum of two non-negative terms. So the left-hand side has to be non-negative. Likewise for the right-hand side, and that's going to happen when c is greater than or equal to negative 3 and less than or equal to positive 3. Okay, now ruling out the cases when c is either 3 or negative 3, I can go ahead and divide both sides by 36 minus 4c squared, because again, if c is either 3 or negative 3, this right-hand side is 0, and I can't divide by 0. Also note that if that right-hand side is 0, okay, that can happen only when both x and z are 0, so that gives us this single point here, right at the origin for that specific xz trace. But in any event, right, for c strictly between negative 3 and 3, when we divide, I again get the equation of an ellipse, right? An ellipse centered at the origin, and the semi-major axis, that'd be 2 times the root of 9 minus c squared. So notice when I take the square root of the 36 minus 4c squared, this 4 can be factored out, and it can jump out of the root as a 2, so I'm left with a root of 9 minus c squared there. And then I'm going to get the root of 9 minus c squared, and then a 2/3 in front of that. Why 2/3? Well, the 2, again, that comes from the factoring out of the 4 up here. And then since there's a 9 in front of the z squared, that's going to jump downstairs, and that's going to give us this 3 here. Okay, so I can see that the semi-major axis, that's going to be along the x-axis because this quantity is bigger than the quantity c under z. The semi-minor axis then is along the z-axis. And again, just like in part A, I'm going to highlight the case when c is equal to 0. Okay, so that's when y is 0. Okay, so that's looking at the intersection of our surface with the xz plane. Okay, and if c is equal to 0, okay, these quantities for the semi-major and minor axes simplify to 6 and 2 respectively. All right, so keep that in mind. Move on then to part C. All right, so again, it's really similar to these other two. So now here, right, if c is strictly between -2 and 2, okay, sorry if this is cut off here just slightly, but this is c is greater than -2 and strictly less than +2. Okay, I can go ahead and divide both sides of this equation by 36 minus 9c squared. Again, I can factor out, in this case, a 9, and then it will jump out of the root as a 3. So I get this equation x over 3 times the root of 4 minus c squared, quantity squared, plus y over, and now I have a 3 over 2 times the root of 4 minus c squared, quantity squared. And why is there a 3 halves there? Well, again, the 3 comes from the factoring out of the 9. And then I have a 4 in front of the y squared here. So that's what's giving rise to this 2 down here. All right, so yeah, family of ellipses again. And if c is 0, okay, we're looking at the intersection of our surface with the xy plane. And these expressions for the semi-major and minor axes, they simplify to 6 and 3 respectively. Okay, great. So now let's go ahead and sketch our surface in R3. All right, so if we put this all together, right, if I'm looking at the YZ traces, okay, you want to think about slicing our surface with planes parallel to the YZ plane. And I'm going to get a family of concentric ellipses when I do that. Ah, okay. So if I chop this surface here like this with planes parallel to the YZ plane, I'm going to see this family of ellipses. Now if I chop, right, with planes parallel to the XZ plane, I also have to get this family of ellipses. It's a different family, of course, but it's another family of ellipses. And then likewise, when I chop parallel to the XY plane. So when you put all those together, you're going to get what looks like a football, essentially. Okay, now let me put in these specific traces that we highlighted along the way, right? These are the intersections of our football, what's called an ellipsoid, with the YZ plane, right, from this one. So that's going to give us this red ellipse right here. And then this cross section, that's the intersection with the XZ plane, so that's here in green, that's that ellipse. And then from C, right, for the YZ trace, if I set C equal to 0, that's going to give me the intersection of our ellipsoid with the XY plane. So that's what you see here in blue. All right, so this football-shaped looking surface, again, is what's known as an ellipsoid, and that's an appropriate name, right, given the fact that all of these traces, right, are ellipses. All right, great. Well, that's going to do it for this question. Thanks so much.